Okay, we're going to look at the logarithmic functions homework. So first off, how do you read this equation? It says x is equal to log base b of a. And what does it describe? Well, it describes an exponent. And so we're looking at this, meaning a base of b to that power x will equal a, which is the argument. So, for example, if you wanted to see an example of that, we have that log base 5 of 25 will be equal to 2, since 5 to the second power equals 25. So if we want to convert the following equations between exponential and log form, we have this first one that says we have 4 to the second power equals 16. So in log form, we would write log base 4 of 16 equals 2. So in other words, 4 to what power gives 16? That exponent is 2. So this next one, we have 3 to the 4th is equal to 1. So we would write log with a base of 3, because that's the base for our exponential form, of 81 equals 4. So then the next one, we're looking at log base 27 of 3 equals 1/3. So this is saying that we have the base of 27 to the 1/3 power equals 3. And just a little reminder on that one. Oopsies. Okay, so we're looking at the next one. 5 to the negative 2 power equals 1 over 25. And so that one is saying that we have a log with a base of 5, and our outcome is going to be 1/25. So it's saying what power, which would be a negative 2. And the next one, we're looking at log base 8 of 1 equals 0. So that's a base of 8 to an exponent of 0 will get us 1. So then lastly, in general, if we have an exponential equation, b to the x equals a, we're going to rewrite this as log base b of a equals x. So b to the x power equals a. So next we're looking at evaluating the following logarithms. So we need to think about what it means to be a log. It's an exponent. So we're looking at 3 over 2, that's our base here, to some power, we don't know, that's the question, has to be 4 over 9. So when I look at that, I see 3/2 is related to the 9 and the 4, like it's the reciprocal and then squared. So remember that a negative exponent makes us flip and get that reciprocal. So that's got to be a negative exponent, and because they're squared, it will be a negative 2. So the answer to this question is negative 2. For this next one, we're looking at a base of 5. So again, to some power, will have to be equal to square root of 1 over 5. So remember, we see the square root, that we can write that as an exponent. So this is actually 1/5 to the 1/2 power. So again, we see that reciprocal going on there with the 1/5. So that means that x here will have to be negative. That gets us the reciprocal. And then we need to have a 1/2 to get that 1/2 power. So log base 5 of the square root of 1/5 will equal negative 1/2. For part 4 here, it wants us to find the domain of these logs. So remember that our argument, so this little guy right inside here, has to always be positive. It cannot be negative or 0. So let's think about that. When is x squared minus 16 going to be greater than 0? Well, we know that if x squared minus 16 is equal to 0, that happens when x is 4 and negative 4. So there's a couple other ways to think about this. Remember when we were solving our quadratic inequalities, we would think about those important numbers, that negative 4 and 4. Those were our zeros for the quadratic x squared minus 16. And so that's really a parabola pointed upward like that. So we know that to the left of negative 4, it's positive, and also to the right of, to the left of negative 4, we're positive, and to the right of positive 4, we're positive. And then right in the middle between negative 4 and 4, we dip below the x-axis, so we're negative there. So if we're trying to stay positive, the part that we're going to be concerned with is going to be this little section and this little section. So in interval notation, that would mean from negative infinity all the way up to negative 4, not including negative 4, and then from 4 to infinity. Now we look at this next one. It says natural log, but we know that that's just a log with a base of e, so we're still concerned with making just the square root of x plus 5 minus 1 positive, or bigger than 0. So if you think about when that's happening, the square root function, well, let's think about this for a second. Let's draw a picture. And so what we have is this graph that's been shifted to the left 5 spaces and down 1, and then it shoots off, if you remember. And so if we want to think about when that's bigger than 0, it's this whole section up here. So again, we're going to be concerned with, well, where does that actually equal 0? So let's try and solve this equation. We have the square root of x plus 5 minus 1 equal to 0. Well, that's only equal to 0 if the square root of x plus 5 equals 1. And then that only happens, well, we can actually undo these operations to see it happens when x plus 5 is equal to 1. And so that's going to happen when x is equal to negative 4. So we know that from negative 4 onward is going to be positive because we'll be living above the x-axis. So in interval notation, that's going to be negative 4, not including that guy, all the way up to infinity. All right, we're going to look at 5 and 6. These ones are graphing the log functions. So remember what we said, that if you're going to graph a log function, you want to think about its inverse. So the parent function that we have going on right here is going to be y equals log base 3 of x. That's our parent. And so if we think about the inverse of the log is the exponential function. So that's going to be 3 to the x. And the reason that we head towards the inverse, because that's a little bit easier to graph. So if we want to input the values like 1, 0, negative 1, if you put a 1 in, you're at 3, 0 in, you're at 1, and negative 1, you're at 1/3. So then if you remember the inverse, since it's the inverse, we're going to have the table for log, without too much thinking, is going to have 3, 1 on it, 1, 0, and then 1/3, negative 1. It's just interchanging those values. And so when we go to plot the parent function on here, we're going to plot the points 3, 1, oopsie, 3, 1, here we go, 3, 1, and then 1, 0, and 1/3 we're at negative 1, so we know that the parent function is kind of doing this thing. And so what we would like to do next is actually do the transformations. So we have a couple of transformations going on here. We have the negative in the front, and that, remember, it's going to reflect across the x-axis. And then we have this guy inside. He's moving us to the right 1 because he's affecting our x values. And then we have this guy, which is going to shift the whole graph down 3 spaces. So if we first start by moving the vertical asymptote, it's going to be right through positive 1. And then individually, I'm going to take each of my points and think about reflecting them. So the 1, 0 is already going to stay here. This guy is going to have to flip down and be at the 1 now. So just the reflection part would have us, well, I guess we need to shift to the right one also. So moving to the right 1, down 3 spaces, right 1, down 3 spaces. Well, overall, our graph is going to do that if we do it all in one step. So I reflected it and I switched it to the right 1 space and also down 3. And so again, going down here, our parent function is going to be log base 3 of x. And our asymptote is going to be the line x equals 1. The domain for this guy is going to be 1 to infinity, which I hope makes sense because we can only take log of positive stuff. And so we have the -1 going on in there. And then our range is going to be from -infinity to infinity. Okay, moving on to the next one. This time, our parent function, I'll write it down just on the bottom here, is going to be log base 2 of x. And so if we're thinking about the inverse of that, that will be a 2 to the x function. And so if I think about my table of values for the inverse, which again, a little bit easier to think about, we put in a 0, that puts us at 1, we put a 1, we're over at 2. So that means for our parent function, we're going to have the points 1, 0, and 2, 1 on it. So I'm going to plot those guys, 1, 0, and then 2, 1, and again, I'll make it dotted. And we have a vertical asymptote. That's the y-axis. And so the transformations that we got going on, we got to stretch vertically. That means our y values are tripling. And then we have a negative inside, which is going to reflect over the y-axis. And so all of our x values are going to have to change from positives to negative, or negative to positive. So if we think about the reflection part first before we stretch, if we're going to be at 1, it's going to reflect and now be at the -1. 2, 1, it would now be at -2 up 1. And so you can kind of see, I'm just going to draw it dotted so you can see that's the reflection with the vertical asymptote still on the y-axis. So then last thing we need to do is stretch it. So all of our y values are going to have to triple. So if this first y value here was at -2, 1, it's going to be now at -2, 3. And this one won't do anything really because its y value is 0. So you can kind of see, final answer here, this would be our graph with a vertical asymptote on the y-axis. Okay, so we know that our asymptote is going to be x equals 0, and our domain now is going to go from -infinity all the way up to 0. Our range is -infinity to infinity.